Alright, so today we're going to be talking about different tests, different tests for convergence and divergence of integrals. And so we've noticed that before we could have determined whether an integral converged or diverged if we evaluated that integral and then took the limits of the antiderivative of the integral and saw if it tended towards infinity or if it converged to a finite value. But we don't always have integrals that we can analytically evaluate. And for example, let's say we wanted to find out whether this integral from 1 to infinity of e to the minus x squared dx converged or not. This integral, as it turns out, there's no simple formula for the antiderivative of e to the minus x squared. And so we cannot readily determine whether or not this integral converges or not through our old strategies. And that's where specific tests come in that help us determine whether some integrals converge or not. And these tests can help us determine whether or not integrals converge without actually having to explicitly evaluate them. And so the first test we're going to be talking about is called the direct comparison test. And the direct comparison test states that let f and g be continuous on the interval from a to infinity, and with 0 is less than or equal to f of x, and that's less than or equal to g of x. So g of x is always greater than or equal to f of x for all x greater than or equal to a. So on this interval, g is always upper bounding f of x, and that's the whole point. Then we can say that the integral from a to infinity of f of x dx converges if the integral from a to infinity of g of x dx converges. And similarly, the integral from a to infinity of g of x dx diverges if the integral from a to infinity of f of x dx diverges. So I'm going to take a moment to kind of motivate why this is true. And that's because, like, let's say we had some g of x right here, and we're told that g of x is upper bounding this other function f of x. So this bottom function over here is f of x, and this upper bound is true from the interval of a all the way towards positive infinity on the x-axis, right? If I knew that g of the integral from a to infinity of g of x diverges, that's just me finding out this whole shaded region area, right? And if that shaded region converges to a finite value, it must make sense that if I were trying to calculate the integral of f of x on that same interval, which calculates this bottom shaded region, just like geometrically, that shaded region will evaluate to a lesser value. And if I already know that the integral of g of x converges to like a finite value, then another value less than a finite value must also be a finite value. And therefore, if we are able to upper bound a function, if we're able to upper bound f of x and prove that that upper bound, which in this case is g of x, if that upper bound converges, then our other function also must converge. And so that's the first statement, and that's the intuition behind why that's true. And you can kind of make the same argument for the second statement. If a smaller function diverges, then a larger function, which is our upper bound, being g of x, that must diverge as well, because its area always takes into account the smaller function's area, and it'll add a bit on top of that. And so if that small portion already diverges, then the addition does not really help us, will not help us converge. So if the smaller portion, being f of x, will diverge, therefore g of x must also diverge. And so hopefully that kind of gives the intuition behind the direct comparison test. And so what it's doing right here is the direct comparison test allows us to evaluate whether like these hard integrals, such as the mode like the this example over here, converges or diverges by upper bounding it or lower bounding it by an easier function, and then evaluating and then like if we had some knowledge on whether that upper or lower bound diverges or converges, we can use that to determine whether that original function converges or diverges without actually having to ever evaluate the original function. And so, with the knowledge of the direct comparison test, let's actually determine whether our original example of 1 to infinity of e to the minus x squared dx converges or diverges. So the first thing we need to do is we need to upper bound this this well, we need to find out whether this integral converges. That's the question. And to do that with the direct comparison test, we need to upper bound this integrand. And so on the interval of 1 to infinity, right, at the value of 1, e to the minus x squared is simply 1 over e. And a suitable upper bound that has an easy integral is e to the minus x. And e to the minus x at the value 1 takes on the same value, but for all the other values on the positive x-axis from 1 to infinity, e to the minus x is always greater than e to the minus x squared on, or always greater than or equal to e to the minus x squared on 1 to infinity. And the way to see that is e to the minus x is simply e to the 1 over e to the x. And this is 1 over e to the x squared. And the idea is to determine whether, like, what the directionality of the sign is, we simply have to compare e to the x versus e to the x squared. And since on 1 to infinity, x will always be less than or equal to x squared, that implies that e to the x will always be e to the x will also always be less than or equal to e to the x squared, because we're just applying like a monotonic transformation. And because the denominator of this left function will always be less than the denominator of the right function, that implies that the left function will always be greater than or equal to the right function. And so we have proved that e to the minus x is a solid upper bound on e to the minus x squared. And so we can use the direct comparison test. And what the direct comparison test tells us that if we can see whether or not, if the integral from 1 to infinity of e to the minus x dx converges on, if this integral converges, because it's an upper bound on e to the minus x squared, if this bottom integral converges, then it must imply that this original lower bound or lower equation should also converge. So let's see if this equation converges or not. When we want to evaluate the limit of this, it's the same thing as limit as b tends to infinity of 1 to b of e to the minus x dx. That's the same thing as limit as b tends towards infinity of negative e to the minus x from 1 to b. Same thing as limit as b tends towards infinity of negative e to the minus b minus negative e to the minus 1. And as b tends towards infinity, this will just tend towards 0, and then this will just tend to, this is a constant, so this will just be 1 over e. And 1 over e is a constant value, so because this evaluates to a finite value, we know that this converges. And since e to the minus x is, since e to the minus x is always greater than or equal to e to the minus x squared on the interval of 1 to infinity, our original equation right here, integral, also converges. And this is through by the direct comparison test. So hopefully that made sense for the direct comparison test, and let's just do a few more examples. So the first example is to see whether or not the integral from 1 to infinity of sine squared x over x squared dx converges or not. And the first thing that you have to do when we're trying to use the direct comparison test is to find out a upper bound on this function. So sine squared x over x squared. We know that sine squared x will always be, so sine squared x is always less than or equal to 1, and it's always less than or equal to 0, because sine x is always between -1 to 1, and then sine squared x will just be like taking the square. And therefore, since the maximum value sine squared x will always take on is 1, we know that sine squared x over x squared will always be less than or equal to 1 over x squared. And essentially, we can now find the integral of 1 from 1 to infinity of 1 over x squared. And this statement over here is just true on all the intervals, so it must be also true from 1 to infinity. And so the integral from 1 of 1 over x squared dx from 1 to infinity, we've proved this before. That when the power function, or when a power function has a when a polynomial power function has a degree greater than 1, it must converge. And so we know from prior fact that this converges because there's like a power function with p being the degree, p equals 2, and p equals 2 is greater than 1. So this converges, and therefore by the direct comparison test, so does the integral from 1 to infinity of sine squared x x squared dx. All right. Now let's prove whether or not this function, or this integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx diverges or not. And the first thing I notice is that 1 over, well, so you always should look at the integrand and analyze it. The first thing I notice is that like the basic power of this and the order of growth of this function is just the same as 1 over x. And we know 1 over x diverges. And so I think like through that intuition, we're trying to prove that this function will diverge, because the idea is 1 over the square root of x squared minus 0.1 is always greater than or equal to 1 over x. And this is true because you can rewrite this original integrand as 1 over x squared times 1 minus 0.1 over x squared, and the square root of that. And that's the same thing as 1 over x times the square root of 1 minus 0.1 over x squared. And notice that compared to 1 over x, on the interval from, on 1 to infinity, on the interval of 1 to infinity, this second term over here will always be less than or equal to 1, because as x tends towards infinity, this term in the square root tends to 1, but it is originally less than 1. And therefore, this is this left fraction is basically x times a value less than 1. And so that must be always greater than or equal to the value of 1 over x times 1, because this denominator on the right side is always greater than the denominator of the left side. And therefore, our left fraction is always an upper bound of the right fraction. And so we have shown that our left fraction is an upper bound of the right fraction. And through the limit comparison test, if we can show whether or not, if we can show that 1 over x dx diverges on this interval, it must mean that the original function diverges. And we know that this function already diverges because here the degree is 1, and when the degree is 1, it diverges. You can also show it by evaluating this to ln x, and you'd get like ln limit as x tends to infinity of ln x, which just equals infinity. And so because our bottom function diverges, the upper bounding function, this being this, also diverges through the limit comparison test. All right, or not the limit comparison test, through the direct comparison test. So we have shown the direct comparison test, and there's one more test that I want to talk about, and this is called the limit comparison test. And the limit comparison test says that if positive functions f and g are continuous on the interval from a to infinity, and the limit as x tends to infinity of f of x divided by g of x is equal to L, where L is not equal to 0 and also L is less than infinity. So L is a finite value that is not 0. And if we remember the orders of growth equation, that just means that f and g are growing at the same order. Then it implies that the integral from a to infinity of f of x dx and the integral from a to infinity of g of x dx either both converge or diverge. So essentially what the limit comparison test says, that if two functions f and g both have the same order of growth, and that's why their limit evaluates to a finite value that is not 0, so they have the same order of growth, and if you don't remember what that is, you should look at that order of growth video, but they have the same order of growth, then they either will both diverge or converge because they grow at the same order. And so again, like, the reason why this test is helpful is because sometimes one of these functions, f or g, might be hard to, like, it might be hard to evaluate whether that integral converges or diverges. So we can find out a simpler function that shares the same order of growth. And once we can share that order of growth, that can we can evaluate the simpler function to see whether or not it converges or diverges, and then we can use that fact to make our, or to come up with a answer on whether our original function converges or diverges. So let's utilize the limit comparison test. So we want to find out that whether or not the function from 1 to infinity of dx over 1 over x squared converges or diverges. So the first thing we must do is we must find a function that shares the same order of growth as 1 over 1 plus x squared. And an easy way to do this is we just remove all these like extraneous terms and just look at the highest degree term. So a function with the same order of growth should be 1 over x squared. And then to just prove that, if you haven't seen this before, is the limit as x tends to infinity of 1 over x squared divided by 1 over 1 plus x squared is simply equal to the limit as x tends to infinity of 1 plus x squared divided by x squared. And we just look at the highest degree terms and to evaluate the limit, and the limit as x tends to infinity will be 1 since the coefficient of both of these are just 1. So that's our limit. And so we see that this limit evaluates to a finite value, and that means that we can use the limit comparison test. And if the limit from 1 to infinity of 1 over x squared dx converges, it must mean that our original function's limit must also converge. And because the degree of 1 over x squared is 2 over here, this is p is equal to 2, we have shown that when p is greater than 1, this function, or this integral from 1 to infinity converges. So this converges. Therefore, by the limit comparison test, the integral from 1 to infinity of dx over 1 plus x squared also converges. And notice that instead of evaluating like tan inverse, this made our life much easier and faster, because we could have just determined whether or not this converges instead of dealing with inverse trig functions and then finding out whether or not this converges or not. Let's do one more example of comparison test. And if you were to actually like evaluate what these two integrals converge to, they don't necessarily converge to the same value. The comparison tests don't tell you what value they converge, what values our integrals converge to. It just tells us whether or not the integral will converge or not. So that's one important fact to remember, which sometimes confuses others. All right. All right. So let's show whether or not the integral from 1 to infinity of 1 over e to the x minus 5 dx converges. We know that 1 over e to the x minus 5 must have the same order of growth as 1 over e to the x, and that seems like a simple integrand for us to evaluate. So the integral from 1 to infinity of e to the minus x dx, that is simply equal to the limit as b tends to infinity of minus e to the minus b minus e to the minus 1, and this will just become 0, and then I think we've shown this before, but this is just e to the minus 1. So we have converged to a finite value, and so because the integral of 1 over e to the x on 1 to infinity converges by the limit comparison test, this integral over here that our problem was asking about also converges. So yeah, that was the limit comparison test and the direct comparison test. And so hopefully you guys can notice how they can serve as easy tests and easy ways to find out whether or not integrals can converge or not.